Hi guys, I have a small little bite-sized riddle for all you Newton fans out there. I like Isaac Newton, he was Sir Isaac Newton indeed. He was a very smart man, I respect him, I respect Einstein as well, but we all have our share of mistakes, and he was one of the pioneers of science, of modern science, Newton, maybe the pioneer, now one of the pioneers of course, to be honest, I'm more of them. There were more people like Newton who were smart enough to see things which we are still baffled about, how they could in those days. But Newton had his share of mistakes, so I have a little riddle for you. And here it is. Now, if you're in classical mechanics, you know these formulas. You see, force is mass times acceleration, and work is force times distance traveled. So you know these two. And you can combine those two, getting this: work is mass times acceleration times distance traveled. These two combined makes this. Only thing I do is take this m times a instead of an f. So you take the f out, m times a, you get this. This is the same thing. M times acceleration of gravity, height, that's kinetic energy, and here's, of course, as I told you, work is mass times acceleration times distance traveled. Now, in order to simplify a formula, I like to use expressions like work and energy are both the same thing. They are both expressed in joules. So get the G from joule for work, get the M in kilograms, mass kilograms, acceleration meters per second square, and distance traveled meters. And when you simplify that, you can say meters, and so you get meters per second, you can multiply them, and then you get meters per second square both, right? And it's mathematically correct to do this, which makes the final outcome: kinetic energy is mass times velocity square. EK is m times velocity square. However, according to Newton, there's a half. So my question is, if you're a Newton fan, what's the half doing there? If you think Newton is right, well, mind you, Einstein, which is also a very smart person, as we know, agrees with me. This is mine. Energy is mass times delta velocity. Einstein says energy is mass times c square. I say this because c is in this universe a delta velocity, and in another universe c might be slower, so then you get another formula. So this is more universal in my book. This is a small difference, but we agree both, and I guess you agree that this is the right formula for energy, and so is this. So where did Newton go wrong? Because I agree, you agree, Einstein agrees, and even the rules of classical mechanics, even those formulas, agree. So where did the half come from? Later on I'll give you the answer. Just put it on pause so you can check these formulas. You can check this if I did it right or not. Did I make a mistake? Tell me. Just put it on pause, and then you can play further and see my explanation. So you're still here. Yeah, the half, where does it come from? Well, the explanation is very simple. Our planet is just too damn big. That's the explanation. Because that mistake, that mistake wasn't made when this formula was made up. No. That mistake was made way before that. It was made when we created scales. And when we started using scales to determine the mass of an object, because that's totally wrong. A scale, like so, is perfect for measuring the force of gravity. You can stick on a kilogram, a calibrated kilogram on this thing, and you can put it on the planet Earth, on the moon, on Mars, in outer space, any planet, any position of that planet, and it will give you the force of gravity. Or, of course, you have some centripetal force, but okay, it's a very good detector for gravity and measuring its force. The thing is, that kilogram, that mass of that kilogram does not change, but despite the mass not changing, the readout is different. And I know we have this agreement that we should mass be established on our planet Earth. And maybe that's why there's so many alien visitors, because they all have scale and they want to calibrate that scale, so they need to go to planet Earth to do that calibration. Come on. No, that's a stupid, very stupid rule. Earth isn't some special planet in our system when it comes to calibrating things. It's nonsense. It's strange to think that. But as I said, nice thing to detect gravity, but and measure gravity, but useless for mass, because the readout changes wherever you go. Now you can also establish the mass of an object using its inertia. Shaking it about, you can feel its inertia, or on a centrifuge, you can get this centripetal force, and then measure that centripetal force and also measure its mass. And the benefit of that is that a centrifuge works perfectly on Earth, on the Moon, on Mars, any planet at all, or even in open space. It will work everywhere, and it will give you every time the same outcome, the exact mass of that object. So a centrifuge is much more, much more precise. But unfortunately, we started out with using scales, because a scale is easy, not so cumbersome as a centrifuge. So we started out using scales and balances and stuff to determine the weight, mass of an object. So we started out wrong. You know, our planet is as such, I said it's too big, is as such that my actual mass is 40 kilograms. But my scale says I'm 80. I weigh 80 kilograms according to my scale, but I weigh 40. That's how big our planet is. If our planet was half the size, I would weigh 40 on my scale and in reality. Same counts if you have a steel ball, 1 kilogram, smashed against the wall, because that's what they did with this thing when they checked this formula. This is the more logical thing, but it didn't work on Earth. So they took a ball and they smashed it against the wall, and the imprint was as such that they thought, well, gosh, it's a little. They expect a bigger imprint. They expected more energy to be in that ball at that speed. I'm sure they measured it using a spring or something like that, but they looked at the imprint, this ball, something is wrong with that. How can you fix that? Well, you know what, let's divide the outcome in half. And there you go, a half. Problem solved. No, not solved. We fixed a problem on the formula for kinetic energy. Well, we should have fixed the scales. That was the problem to begin with. We have the wrong way to determine mass. So that's where the half comes from. The half comes from, it's a correction factor for planet Earth. That's the half. If we had a smaller planet, we wouldn't have that problem. If we had a planet half this small, we wouldn't have this problem. And say if Newton was born on the moon, his formula would be, for kinetic energy, would be E kinetic is 3 mass times velocity square, if Newton was born on the moon, because of his low gravity. So he has to compensate. It's silly to use compensation factors for planets. It's silly to think Earth is some kind of exceptional planet throughout the universe where everybody goes to calibrate their scales. It's also nonsense. Mass is not established by using a scale. You can only establish mass using a centrifuge. So I like scales, no problem with scales. If you buy some potatoes, some rice in the marketplace, the scale's fine. But a professional does not use a scale. A professional uses a centrifuge to determine the weight, or the mass of an object, since weight and mass are unrelated. Weight is only the force of gravity. Weight says something about the field of gravity, and mass says something about the number of nucleons within an atom. So there's a difference. And that's why there's a correction factor of 1/2. Thank you.